guys, how's it going today? In today's video, we'll look at limiting reagents, which is a crucial part of lab chemistry and our second to last lecture in the stoichiometry unit. Let's get started. To start today, we're going to talk about what a limiting reagent actually is and why it is important. We'll then look at how to determine the limiting reagent in a chemical reaction, and finally, we'll practice determining the leftover reactants when a reaction is performed. Let's start out with a real-world example. Let's say you're trying to make a fruit salad. You want to make this fruit salad using pineapple, pear, apple, banana, and grapes, which honestly doesn't sound very good to me, but whatever. In your kitchen, you have 4 pineapples, 3 pears, 20 apples, 1 banana, and 300 grapes. You counted. Not sure why. To get approximately even slices, you can cut your pineapples into 30 slices each, pears into 15, apples into 16, bananas into 25, and grapes can be cut in half. And since you're a rational, sane human being, you want to make your salad with a 1 to 1 to 1 to 1 to 1 ratio. Now, those of you who really love math may have already done this calculation, but the total number of slices you could have of each fruit are 120 pineapple slices, 45 pear slices, 320 apple slices, 600 grape halves, and 25 banana slices. That means that, assuming you really want that 1 to 1 to 1 to 1 to 1 ratio, you can only include 25 slices of each fruit in your salad. In this case, you have the fewest possible slices of banana, making it limit the amount you can actually use of the others. If we think of the fruits like reactants in a chemical reaction, the banana is all being used up first, leaving the other fruits unable to react further. Perhaps a more obvious example of this is when you make a campfire. If you leave the wood burning without putting it out, eventually the fire will die on its own. But it's not like it ran out of available oxygen. The carbon and hydrogen in the wood all reacts, limiting the reaction from moving forward. Here's an example in the form of a chemistry problem. You have 12 moles of H2SO4, or sulfuric acid, and 2 moles of NaOH, or sodium hydroxide. Which will you run out of first? We could do a bunch of fancy math to prove this, but a quick look at the balanced chemical equation tells us that we're going to run out of NaOH first. The chemical equation tells us that every mole of H2SO4 needs to react with 2 moles of NaOH. In order to react 12 moles of H2SO4, we would need 24 moles of NaOH. We only have 2, so we can only react 1 mole of the sulfuric acid before our NaOH runs out. This means that NaOH is our limiting reagent. We should probably actually define what a limiting reagent is. And a limiting reagent is the reactant that is totally consumed during a chemical reaction. It limits the amount that the reaction can occur, and we can determine this limiting reagent in a given reaction using the balanced chemical equation. Let's try some practice. This first problem says you have 2 moles of C3H8 and 8 moles of O2. Which is the limiting reagent? We know that for each 1 mole of C3H8 we need 5 moles of oxygen. So for 2 moles, we would need 2 here, we need 10 here, 6, and 8. So in order to react 2 moles of C3H8, we need 10 moles of oxygen. We don't end up having 10 moles of oxygen, we only have 8. So that means that oxygen, O2, is going to be our limiting reagent. The second part asks, how many moles of the non-limiting reagent are left over when the reaction runs? Now, this is a little bit trickier. Our ratio of C3H8 to O2 is 1 to 5. So for every 1 mole of C3H8, we can use 5 moles of oxygen. Now, we have 8 moles of oxygen. So we multiply this by 8. This is 1 mole C3H8, and this is O2, times 8 moles of O2. Moles of O2 would cancel out, and we are left with 8/5, or 1.6 moles of C3H8 that we're going to use up. Now, we started with 2, so 2 minus 1.6 equals 0.4 moles of C3H8 are going to be left over. So for our second example, we have 5 moles of HCl and 2 moles of zinc, which is the limiting reagent. From our chemical reaction, we can get that our ratio of HCl to zinc is 2 to 1. So we've got 2 moles HCl to 1 mole of zinc. Now, in this case, we have 5 moles of HCl. So we're going to start with 5 moles of HCl. And then we want our moles of HCl on the bottom here to cancel out. So moles HCl, 2, and this one's going to be 1 mole of zinc. So with 5 moles of HCl, we could react 2.5 moles of zinc. we only have 2, which means zinc is going to be our limiting reagent. So zinc is the answer to that first part. Second question asks, how many moles of the non-limiting reagent are left over when the reaction runs? Now, we said that we have 2 moles of zinc. So if we have 2 moles of zinc, let's figure out how many moles of HCl that we can react that with. So 2 moles of zinc times 2 moles of HCl per 1 mole of zinc. Moles of zinc cancel out, and we're left with 4 moles of HCl. So the most we could possibly react with this quantity of zinc is 4 moles of HCl. We started with 5, so 5 moles minus 4, and we're left with 1 mole of HCl as our answer. Unfortunately, in a real lab setting, we can't measure reactants directly in moles. This means we have to do some converting in order to determine our limiting reagents. We have to be able to convert volumes, masses, and molarities of solutions into moles in order to determine the limiting reagent. Once we have determined our limiting reagent, we can also determine how much of each other reactant we will have left over. And as always with these stoichiometry problems, you can never go wrong converting your units into moles as a first step. Let's look at some examples. So this problem asks us, if we react 13.5 grams of aluminum with 100 milliliters of 6 molar copper chloride, what is our limiting reagent? Now luckily for us, the ratio here is going to be 1 to 1, so we just need to determine which one we have more moles of. Now the molar mass of aluminum is about 27 grams per mole. If we have 13.5 grams times 1 mole per 27 grams, we end up with 0.5 moles of aluminum. For copper chloride, we're using a 6 molar solution, which means we have 6 moles per 1 liter. But we're given 100 milliliters, so we need to convert that to liters first. So 100 milliliters times 1 liter per 1,000 milliliters equals 0.1 liters. 0.1 liters. It's hard to tell what this is, isn't it? 0.1 liters times 6 moles of copper chloride per 1 liter. Liters cancel, and we get 0.6 moles of copper chloride. So we have 0.5 moles of aluminum reacting with 0.6 moles of copper chloride. That means that aluminum is going to be our limiting reagent. Now, again, because it's a 1-to-1 ratio, our math is really easy. We can also quickly calculate that we're going to have 0.1 moles of copper chloride left over. And if we wanted to change that back into how much of the solution is unnecessary to be used, we could do that. But that would take time and be extra math, and there's no reason to do that right now. For our last practice problem, we're reacting 22.4 liters of oxygen gas with 24.3 grams of magnesium. We're asked, what is our limiting reagent? Now, if this question was written by somebody who was paying attention, it would have said that this 22.4 liters of oxygen gas is at standard temperature and pressure. We're going to go ahead and assume that anyway. So we know that the conversion for 1 mole of gas at standard temperature and pressure is 22.4 liters. We happen to have 22.4 liters of O2 times 1 mole of O2 per 22.4 liters. And that's going to cancel out. We're left with 1 mole of O2. 24.3 grams also happens to be the molar mass of magnesium, which is in grams per 1 mole for magnesium. We have 24.3 grams times 1 mole per 24.3 grams. And yes, I did round it off. These will also cancel out, and we're left with 1 mole of magnesium. If we have 1 mole of magnesium reacting with 1 mole of oxygen, but the ratio is 2 to 1, that means that we're going to run out of magnesium first, and we're going to be left with exactly half of a mole of O2 left over. That half mole of O2, if we wanted to convert it back into a gas volume, we could just multiply it by this. We'd end up getting 11.2 liters. Let's review. Chemical reactions don't only occur in chemistry class worksheets and are usually done in the real world, where getting the perfect ratios of reactants is nearly impossible. This means that most real chemical reactions will have a limiting reagent, which is the reactant that is totally consumed in a reaction and prevents the reaction from continuing. This will leave leftovers of the other reactants, all of which we can determine through a combination of our awesome knowledge of stoichiometry. This will leave leftovers of the other reactants, all of which we can determine through a combination of our awesome knowledge of stoichiometric conversions, the balanced chemical equation for a reaction, and a lot of math. That's it for this video. I'll talk to you next time.